Okay, this video links to the second part on your mind map, okay, for C3, which is rate of reactions 2. When we talk about rates of reactions, as we said in the first video, it's all about basically how fast the reaction is proceeding, okay, how much product is maybe made in a certain amount of time. When it comes to the second part, we need to start looking at graphs and we need to start explaining, okay, why different factors affect rate. So for a reaction to occur, you have to have two different chemicals at least, okay, within your chemical reaction. And the key thing is, in order for them to actually be able to react, the first thing is they have to be able to collide, okay? And particles will generally collide quite a lot of the time. When it comes to looking at collisions, it also depends on how much energy they actually have when they do collide. So it's not just about the collisions, it's about the energy that they have. So you could have a situation where two particles collide with each other, two different particles, and because they don't have very much energy when they do collide, they will literally bounce off of each other. And in that particular case, you will get no reaction occurring. If, however, they have enough energy, something that is called the activation energy, when they collide, they will react, they will produce a new product, and a reaction will happen. Collisions that occur, that collide with enough energy and allow a reaction to happen, are called successful collisions. So some collisions are not successful, and other collisions between particles are successful because they have enough energy. Factors that affect how quickly a reaction goes, very important for industry in particular. Two we're going to look at now. The first one is temperature, and the second factor is the concentration. To start with, we'll look at concentration. Concentration will be linked generally to equations where there is at least one solution, okay, as a reactant. When we talk about concentration, we are talking about taking the same volume and comparing how many particles of the reactant are actually there. So the two boxes represent the same volume, and if you have got a highly concentrated solution, let's say of acid, there will be lots and lots and lots of acid particles there. If it has a low concentration, there will be less acid particles. So how does increasing the concentration of a reactant, like an acid, actually affect the rate? Because in a higher concentration, you have more particles in the same volume. This will influence, because of how crowded those particles get, the number of collisions that will happen. So because there are more particles, we get more collisions. Now, just saying more collisions is a C grade answer. In order to make sure you get up to the B or the A grade, you have to talk about collisions within a time frame. So the easiest way to do this is to say that there are more collisions per second. And this applies for every single thing that you explain when it comes to rates of reaction. More collisions per second will create a faster rate. Okay, so higher concentration contains more particles in the same volume. That will cause more collisions per second because they're more crowded, which will cause a faster rate. Temperature is a little bit different because temperature links to energy. If you heat up your reactants, what you are giving is more energy to the particles. So the particles gain energy. What this means is that the particles will move faster. And if the particles move faster, and contain more energy, there are two key things that will happen. The first thing, again, is that there will be more collisions per second because the speed of them has increased. But thinking back to the word that we used earlier, successful collisions, because they have more energy, when they do collide, they're more likely to react. So what we can say is more successful collisions per second. You could use that word on every explanation. And again, because there are more successful collisions per second, the rate of reaction will increase. So temperature, particles gain energy, they move faster, more successful collisions per second occur, and the rate will be faster. In the case of graphs, there are certain key things that you have to be able to basically interpret. So we might have, for example, time proceeding along the bottom, and let's do something similar like volume of gas, like we did in video 1. And you get a very, very similar shaped graph every single time. It starts off quickly, okay? So you've got a quick reaction at the beginning, and that's because you basically got lots of reactant particles at that particular point. As those particles are used and reacted, the reaction starts to slow until eventually, on this particular point, it stops. If they ask you when the reaction stopped, you have to look at the point where, okay, if we kind of carried on the line here, the point where it becomes a straight line. And then you can work your way down to this point here, where it has stopped, to whatever the time happens to be, okay? So that will depend obviously on your axes. They could also ask you what volume of gas was produced in total, and again you would have to get to the stopping point, bring your line across the volume of gas, and again read what that volume happens to be, okay? Other things that you need to understand in terms of interpreting. The first thing is the gradient, okay, or the steepness of the line indicates the rate. And the steeper the line, the faster the rate. So if, for example, we had a second line like this, this would indicate a faster rate because the line is steeper. Now, what's quite important to notice is although the line is steeper, the line ended at exactly the same point. Both of those lines ending at exactly the same point tells you that the same amount of limiting reactant was actually used. If the limiting reactant is increased, then you would obviously produce more gas, okay, at the end. But if you start with the same amount of the reactant, but you just change the conditions, so for example, this might indicate a higher temperature or it might indicate a higher concentration, then the gradient before it stops at the same point will obviously be steeper.